Hello again, YouTube. It's me, Zeth, if you're new. It's time for another topic review. So, if you're new to this playlist or my channel in general, I am currently enrolled as a student at the coding bootcamp called the Flatiron School, and I'm in phase 3 of 5 total phases. And as a new sort of study habit for this phase, I've been vlogging about what I'm learning in every module along the way. So that's what this video is. I'm reviewing module number 28. So it's the 18th one in this, or no, sorry, the 8th one in this phase. It's about 10 phases, or 10 modules per phase. So anyway, as usual, I don't do this on behalf of or for Flatiron or anything. This is strictly me for my own purposes of practicing my knowledge and just like sharing cool stuff I learned. There is some pictures and things that I use from the Flatiron curriculum. So again, just like all credit to them. If you're curious about more of that, I'll have the link to my GitHub repo as well as Flatiron School's website in the description below. And you can find like the licenses and everything for the Flatiron School stuff. Like there's every module has like a Learn Code folder. So if you look in that Learn Code folder, you can find all the like licensing and like contribution stuff if you're curious about that. So without further ado, let's get into the topic review for today. I'm kind of blocking the thing there, but you can see that says classification. So the last module we talked about, was it decision trees and regression trees and that sort of thing. And so this module is a little similar in the sense that we're talking about classification again, but just a different type of classification model. So this one is called KNN, or K nearest neighbors. And basically, K nearest neighbors is a classification algorithm that classifies a given data point based on some statistics about the other data points within a certain range of that given data point. On the simplest level, that's basically like how it works, and how you measure like the distance and like what you assign for the value k, and all that sort of stuff can be sort of adjusted and explored as in the form of like hyperparameters. Very similar to how I did some of the hyperparameter tuning, showed some of the for loops and stuff in the last video. So that's broadly speaking what K nearest neighbors is. K is like generally like arbitrarily, or at least you usually start with like just some arbitrary value for K, and then you explore how different statistics about the model improve or worsen as you change the value for K. But generally speaking, as K approaches infinity, or as K increases, it's going to lead to underfitting like this, where you don't have quite, you're not drawing quite distinct enough of a boundary between like your two sort of groups that you're trying to classify between, right? It's also important to note that values for K are usually only, or they're pretty much always only odd numbers. Reason being that if you have an even number for K, you might have like equal probabilities or equal data points like on either side of your like sort of like what, like I guess this would be it's not a regression line, but this curve that you have here that represents like your classification. You want to pick one or the other, like as a data point on one side of it or the other, basically. So because of that, you use like an odd number valued for K. K is the number of like how many data points with the closest to that like point. So if like K is 5, like, and this is our data point here, it's gonna capture like 1, 2, 3, 4, and like one of these guys, depending on whichever one's technically closer. So yeah, it's not doing it by like space or area like within this curve necessarily. It's doing it by just like the count of data points themselves. So if you use an odd value for K, then it's going to kind of more automatically like make a decision or classification like on one side or the other. Anyway, so that's a little tangential. As k increases, that will at some point start causing underfitting, and if as k approaches 0, k is going to overfit. Obviously, k can't be 0 because then you're only going to have the one given data point anyway. But from whatever like hypothetical like maximum, it like might be in the realm of feasibility, as it decreases at some point once it passes like some extreme, leads to overfitting. And so you can find the optimum value for k by iterating through different models with different values for k, just like you do like any other hyperparameter. Just like I did like in the last video with those for loops for like the maximum depth and minimum sample split, like that sort of thing. So the general workflow for optimizing a KNN classifier, you take a given data point and a given value for k. This is like generally how the algorithm flows. This isn't like how you would code it or how you would build it necessarily. But anyway, take a given data point and a given value for k. You take the k nearest point. So if your value is 5, you're going to take like the 5 closest data points to it, and you're going to predict a label for that point, the initial one that you were given, based on some metrics or some statistics about those other data points captured by your k value, right? So if we're calling it classification, we're talking about like what's the most common label like within your like sample or your training data. That's usually what we mean by like classification. Versus regression is we're taking like the mean of like say the error term or something for those points captured by your k value. So that's kind of like the big distinction between regression and classification here is regressions for like continuous values versus classifications for categorical values, generally speaking. With either one of those, you can do like a k nearest neighbors algorithm, and you can also use you probably should at some point as you like iterate and improve your model, use weighted averages based on like the distance. So basically, like the further away a data point is from the data point that you're trying to predict, the more it's going to penalize how much that data point contributes to the average. So if you're looking at the average of like, or just like what the average like value is for all those like data points captured. Say we're dealing with regression, right? It's going to weight the input of like your furthest data points into that average. So it's not going to be just like a strict raw average that you do by hand, basically. So that's probably a good idea. And at some point, if you're like iteratively improving your model, you're probably going to use weighted averages at some point. And it's going to be penalized based on like the distance the predictor point is from like the target point. Anyway, so you can improve your model performance by iterating over select hyperparameters. And again, this is like basically the same as what you saw in the last video. So we have like our precision, accuracy, recall, F1 score. In this module, I don't think I've talked about log loss before, but that was like another metric that we used for the KNN models at least, to measure the predictive capability of the model. So I'm trying to think of like a similar metric for log loss that I used for decision trees and regression trees. Regression trees, I guess, like the like your what residual sum of squares maybe. It's a way of like defining or quantifying your like error term for like the model like in general, right? So you have these different metrics that you look at, and basically like you go through a for loop, and you create in terms of code, you instantiate like a class object as your like KNN classifier, and then there's different parameters that you can pass in for that, like your value for k, your value for there's different ways of measuring distance, which we're going to talk about in a second, different all sorts of stuff like that. And you just iterate through different inputs for those parameters, and you see how it affects the model. And again, this is just, I didn't like go into the code here because it's like basically it's the same thought process as with the decision trees and regression trees from like the last video. Cool. So let's talk about distance metrics. So this formula you see right here is really just a grown-up version of the x2 minus x1 over y2 minus y1. That whole deal from, you remember from like, 8th grade algebra, where you're calculating like the slope or like the length of a line or whatever. The length of a line, yeah. So there's different ways to calculate distance on a graph. And so Manhattan distance, Euclidean distance, and Minkowski different distance are different formulas used to calculate that distance. So think like Pythagorean theorem, like can calculate if you have like 2 points on the graph and they form like a right angle, which on a graph any two given points like eventually would create a right angle, right? You can use Pythagorean theorem to calculate like that, the hypotenuse there, and so these are basically just other ways of calculating that, kind of for more of like a calculus sort of setting. So anyway, the formula here is like the generalized term or generalized formula that we have for calculating the distance between 2 points. This changes a little bit as you add dimensions to it. But so this is why we have like 1 over c in the top right here instead of like if we were doing like Euclidean distance, we could also write this as like, instead of having that 1 over c, we would have like everything in the parentheses under like the square root. I think it's called a free radical. The square root sign. So anyway, that's getting a little tangential. Basically, you can treat this value c that you see in the formula like a hyperparameter, and you can try, using Manhattan distance or Euclidean distance or Minkowski distance for your models when you instantiate them, and you'll be able to look at like your F1 score or your precision or whatever you're interested in, and you'll see like how Manhattan distance versus Minkowski distance or whatever affects the output of those statistics and those metrics. Minkowski distance is a little weird, but it's also probably like the most like generalized version. So you see where I have like c equals n plus 2. All that really means is that Manhattan distance and Euclidean distance are special cases of Minkowski distance. So we give them, like honorable mention or whatever. But Minkowski distance is really where those come from, and they're just different values for c, right? And then so Minkowski distance could be like c equals 5 or c equals 7 or like whatever. It just has to follow these 2 rules that you see below here, which in the curriculum, the Flatiron people didn't like stress it so much, so I didn't stress about it so much. So I don't like really understand that in a whole lot of depth. Why like the 0 vector needs to have an output or a length of 0 and like whatever. So outside the scope of what I need to learn for this module, but there it is if you're curious, and it's in the notebook, of course. So real quickly, we'll take a little field trip over to here. So this was like the cumulative lab that I went over for this module. So it's kind of like everything in this phase up to now that I've learned. I'm just going to go through here kind of rapid fire style real quick. Again, this is available on the GitHub repo if you really want to dig into it. Anyway, prepare your data for modeling. So we import some CSV file. Sorry, that's not the CSV file. We import some CSV file somewhere up here. Split it into like your predictors and your target column. Do your train test split. Scale the data. See if that does anything useful. So here's how we're calculating log loss, and that took forever. Anyway, so calculate your baseline log loss. You build your baseline model, calculate your like, evaluation metric, whatever one you're using, whether it's a log loss or whatever else it might be for your baseline model. Now here, oh, it didn't save the output of those cells. Okay, this cell took like 170 minutes to run, like over 2 hours to run. So we're not gonna run that again right now. But what it did was it iterated through the range from 1 to 100, and it used that as your k value. In underscore neighbors here is the parameter for our k value. So that is what's going on in this for loop here. Is we're trying different values for k, and then we're calculating our valuation metrics, and we're pinning them to this list here, and then okay, so it did save the cell outputs, which gives us this data frame right here. This is actually, we put that all into a data frame, and then I use the .describe method, and this gives us like our mins and our maxes and like all that sort of stuff. So and then I kind of repeated the same process for my value for C, which in scikit-learn is P for some reason. I couldn't, there's a parameter where you can pass in like the string Manhattan, Euclidean, Minkowski, or whatever, but I kept getting errors on it. Like a key error saying that like the string that I typed in wasn't the same, but I literally copied and pasted it like straight from the docs. So I just used P because it's literally the same thing. Same thing here. This didn't take nearly as long because I only had to do it 3 times, but I'm also like thinking now I should have gone for like 4, 5, 6, or 7. Anyway, same thing here. I picked the one with the least log loss. So basically speaking, the lower your log loss is, the more reliable your predictions probably are. So at each one of these like kind of phases, if you will, I picked the one with the lowest log loss value, which you can see me indexing here. So where k is 18, that's where we have the least log loss for every model from k equals 1 to k equals 100. And same thing here. The P or the C value in like mathematical notation was 1, which is Manhattan distance, which wasn't really all that surprising. It seems like Manhattan distance is pretty common from what I've like observed so far. And I think, yeah, I did like basically the same thing for a decision tree instead. But we've already seen the decision tree before. So that's how you do a k nearest neighbors thing. One thing that I want to learn, or I think would be cool, is there's, obviously there's not a whole lot of data visualization going on here, but it's like a fundamentally like viz-driven like thing, this idea of like nearest. I guess that's not fundamentally visual or optical, but it's definitely like gives it a stronger intuition or more accessible intuition than a lot of the other models do. So I would like to see more, or be able to visualize this sort of thing a little bit cooler. So that is it for module 28, and I was thinking about doing a little bit of Git stuff, showing how I set up like my repos and things, my workflow for that in this video, but I think I might just make a separate video for that. Yeah, so 18 minutes is pretty good. I'm kind of liking the format I've been going with the last couple of videos. I haven't been spending like way too much time just kind of generally reviewing like the broad topics that I'm learning about, rather than actually like trying to code them and stuff on screen. Seems a little bit more economical. So yeah, I hope you enjoyed this. I hope you watched it. I hope somebody watches it. I hope you got something out of it. As always, I highly recommend Flatiron, especially if you're considering data science. It's weird to call it a coding boot camp because we're learning a lot more than just like the code. The code's really kind of just like the substrate for all the stuff that we're learning. So yeah, check out LinkedIn, check out Flatiron in the link below, and of course you can connect with me on LinkedIn, and the link to the GitHub repo is there too, and leave a like on the video and a subscribe, and that would make me thrilled. And until next time, I'll see you in another few days with a video on module 29. Hasta luego.